Okay, so today we're going to be graphing absolute value again, except for this time we're going to be doing something called a dilation. Now, this is where we either stretch it towards infinity or we stretch it towards zero, which is going to be called a compression. And now, this is one of the topics that we're going to get into is we're not really sure whether or not we're stretching the graph or if we're just stretching our perspective. We're going to be unable to tell the difference from this point and in many future lessons. So we're not necessarily going to worry about where this change is coming from. Is it coming from us or is it coming from the math? So let's take a look at our first dilation. Our first dilation is a very simple dilation. We have a negative sign out front. And if we remember, yesterday we said our parent graph always had a perfect diagonal right through the origin. And there's my y equals the absolute value of x. What we're going to do is we're going to see what happens when we have a dilation of a negative number. Well, let's go ahead and let's make a table of values for some numbers that we used yesterday. -2, -1, 0, 1, and 2. So I'm going to plug all of these in to my equation. Now, here's the thing. My equation says I have to take the absolute value and I have to make it negative, which many of us look at and we're like, can we do that? Can I plug in a -2 and get something other than a positive number? Well, let's take a look at the order of the steps. So after my first iteration, when I plug in the absolute value brackets, that negative didn't go anywhere. But my -2 did become a +2. And same thing with each one. My negative didn't do anything, but my -1 is now a +1. My 0 is still a 0. My +1 remains a +1, and my +2 remains a +2, which means that we actually just have negative values. Boom. And so if we graph these points at -2, -2, -1, 0, we see that our graph has completely flipped upside down. And boom, there's our first dilation. We've taken the graph and we're now looking at upside down. Now, did that come from the graph being manipulated? Did we compress it through the origin? Did we change our perspective? Are we now looking at it upside down? That's going to be difficult to prove. So let's just understand that that is a dilation. Some perspective has been changed, and let's move forward. Another common dilation is going to be if we have a 2, which is going to be what we call a stretch. So let's take a look. Let's pop this, our parent graph, onto the grid. Y equals the absolute value of x. Let's see what happens if I have a 2 out front by making an XY chart and using those common values that we've been using. Now we're going to pop each one of those in to our absolute value brackets. I'm going to plug in a -2, -1, 0, 1, and a 2. After my first iteration, anything inside the absolute value brackets becomes positive. And then I double it, which gets me 4, 2, 0, 2, and 4. So what I notice is that my graph, each one of my points has doubled the y value. What was a 2 right here is now a 4 right here. We literally doubled the height of each point. And so it looks like I'm going up 2 over 1 from each one of these. Y equals 2 absolute value of x. And so what was a perfect diagonal of going up 1 over 1 every single time is now a slightly stretched diagonal of going up 2 over 1 each time. So let's see, let's do one more. See if we can't spot a pattern going on here. So I'm going to graph my parent graph that is a perfect diagonal of y equals the absolute value of x. And I'm going to say, okay, what's going to happen with the 1/3? Well, if that made it taller and skinnier, I bet you this is going to make it the opposite. I bet you it's going to make it shorter and fatter. Well, let's try it out. -2, -1, 0, 1, and 2. That's what we have right here. So we have our 1/3 of a -2, -1, 0, 1, and 2. And after my first iteration, everything inside the brackets becomes positive. And after my second iteration, I get a 2/3, 1/3, 0, 1/3, and 2/3. And so I notice that each one of these looks like it's gone down a significant amount. Which in this case, I bet you if I continue that further, 0, 1/3, 2/3, I bet you that would be 3/3. And if I plugged it in, 1/3 of 3 is 1/3 of 3, which is 1. There's my next point. And so what we notice is that there's a pattern going on with this diagonal. I was going up 1 over 1 with the parent graph each time. Now this time, between my origin and my next whole point right here, I went up 1 over 3. So where do I see an up 1 over 3 on my equation? It's the number out front. So I bet you if we use that, we won't need to build a table. We can just find the vertex and follow that slope. So let's give it a shot. Let's see if I can do that to this problem. Well, if my perfect diagonal on my parent function was 1 over 1, and I reflect it across the y-axis, I bet you this one is going to be down 5 over 7. Well, I can't fit that on there, so what I'm going to do is I'm going to say my graph is by 2's, which shouldn't change my parent function, because instead of going up 1 over 1, I'm going up 2 over 2, which is the same thing. So if I do these by 2's, I'm going to put a point in the middle. I'm going to go down 5, 2, 4, 5, and I'm going to go over 7, 2, 4, 6, 7. And I'm going to mirror that. Instead of going over 7 to the right, I'm going to go over to 7 to the left. In fact, this works. We can just simply look at this number right here and see what the rise and the run are. Here we have a rise of -5 and we have a run of 7. If you wanted to test those points, you could. If I wanted to say, can I plug in and get this number? Well, let's see. If I plug in a -7 into my -5/7, -7, that's -5/7 of +7, which cancels out. That is a -5, which is indeed that point right there. If I plugged in a 0, -5/7 of the absolute value of 0, which means -5/7 of 0, which is 0. That point's included. And even if we include a +7, remember, because of the nature of the absolute value brackets, it doesn't matter where we started, it ends up being a positive, which cancels out, and I get a -5, which is in fact that point. So yes, this method does work. And even if we have other translations in the equation, I know that I can read these as a, okay, that's a left 2 and up 2. So left 2, up 2, that's where I'm going to put my vertex. This negative 2 over 1 tells me I have a rise of negative 2 and a run of 1. So rise negative 2 and run 1, and then reflect that in the other direction. So when I go to the right, when I run to the left. And I notice that this works extremely well. So we get this graph. In fact, any graph, as long as we move it and then stretch it, we're good. So even with this one down here, I'm going to be moving it to the right by 4 and down 1, and I'm going to have a rise of 1 and a run of 5 in both directions. So right 4, down 1, there's my vertex. If I rise 1, run over 5, well, that's way over here. If I rise 1, go over 5 in the other direction, I get that right there. So, kind of missed my point there, but let's assume that went through there. So anytime we have an absolute value function, we know the slope and we know the starting point. And that's all we need to graph any absolute value function.